All right, let's get started. So I'm not as mobile today. I strained my knee at the gym, so excuse me if I don't walk around as much. All right, so let's get started. So today we're going to segue to a new chapter, specifically material concerning Chapter 5, which is on scheduling. And so scheduling is a really important concept in operating systems, and making the right choice as far as scheduling is concerned will lead to significant performance improvements. And so, in most general purpose operating systems, like your typical desktop OS, you don't have opportunity to do scheduling. But in many server versions of operating systems, including also Linux, you can tune what are called the kernel parameters. And in doing so, you can alter the way that scheduling is done. So, for the reading for this material, it's only about 28 pages. Please make sure you're keeping up with the reading. And we have 4 weeks left in the semester this week and then next week. Next week is a short week because of the Thanksgiving holiday and because we meet on, no, that's not true. This week and next week. And then the week after that is a Thanksgiving holiday, which is a short week, meaning that we don't meet Thursday, we only meet that Tuesday. And then we have one more week, the first week of December, ending on the 5th. And so thinking of giving an exam for this class a week from today. I always announce exams a week in advance. And this exam would cover material including today, but it'll focus primarily on processes, interprocess communication, as well as threads and just the introductory material on scheduling. I do recognize that I have a boatload of graded stuff to get back to you. I am working on that. This semester I'm overloaded, meaning that I'm teaching extra courses that I wouldn't otherwise teach. That's not your problem, that's my problem, but it does impact my ability to do all sorts of stuff. So please bear with me. I will get some stuff back to you on Thursday, and then next week, Tuesday, clear off everything that I was doing to get you all caught up on the return material. And again, like we did with the first exam, you're allowed one 8.5 by 11 sheet of paper, both sides. And so please just have one sheet. Don't do the thing of gluing two sheets together or having two sheets one side, one piece of paper. Simple rule. Please make sure you follow it. Okay, so there's the reading. Let's jump in to what the objectives are. And so the goal of chapter 5 is to talk about scheduling. Excuse me, and scheduling, as you'll find, is that choice for the short-term scheduler to determine which of the processes is going to get the CPU next. And so going forward, we won't talk about processes per se. If you think about it, a process is nothing more than a single threaded process, right? And so we're going to consider a thread as the unit of schedulability on the CPU, regardless of if we're talking about threads per se or processes. And moreover, kernel level threads are those threads that are seen by the CPU, right? And kernel level threads can be run on the CPU, or you can have custom support on a core or CPU to actually get those threads to run really, really fast. Okay, and so we'll talk about scheduling. We'll also talk about a number of scheduling algorithms, and this is not an exhaustive list. It's just to give you a sense of what the impact of scheduling is. And then we'll also look at details of some of these and look at how you might evaluate some of this. Okay? All right. Any questions? Make sense? Okay. So let's talk about the basics. And so the whole goal when you have a CPU, you want to keep it working as much of the time as possible, right? That's the whole point of spending a lot of money on a computer, especially if you go to the multiprocessing case. You want to keep them working, you want to keep them busy as much as possible. So the whole goal behind scheduling is to try to maximize CPU utilization. For any period of time in which you have stuff happening on your machine, you want to make sure that that CPU is doing something. Now recall, you can have two types of processes. You can have a process that's running so-called compute bound, meaning that it's executing instructions that just does not require I/O devices, right? So maybe you're calculating something, you're doing arithmetic operations, you're doing floating point operations, and so forth. And then there's also a so-called I/O bound process, and an I/O bound process is one that executes I/O operations. So it's going to interact with the I/O controllers, and therefore it's going to wait. And of course, when a thread is waiting, it no longer needs a CPU because it's a waste of CPU cycles, and that thread and the process that owns that thread is kicked off the processor and it enters the wait queue associated with that particular I/O device. And so the idea then, when you're scheduling, is you want to make sure as much as possible that you're keeping the CPU busy. You don't want it to be waiting all the time. And so you certainly also want all your programs to make progress. So some of the times you're going to run processes that are compute bound. Some of the times those compute bound processes will execute an I/O operation and then wait, they get kicked off. Other times you're going to see processes and the underlying threads that become unblocked because they've been on the wait queue for an I/O device and now they're ready to run and enter the ready queue again. Okay, so all of the criteria takes this into consideration. And so let's imagine, and this is a figure, it's from the book, and time increases going down the board, and you have some program that loads a piece of storage or loads some data or some state from some store, some storage, and then it calculates something. Maybe it's doing some addition, doing some operations, and then all of a sudden it needs some information from disk, so it decides to issue a system call for something like reading from a file. Now, of course, that's an I/O operation, and then all of a sudden, this process is now executing I/O, right? So there's another term in scheduling, and we'll introduce this. It's this notion of a burst. And a burst is nothing more than the time between when a particular process or thread is admitted to the CPU to when it returns back to the user for some reason. And so when they talk about process or thread bursts, they talk about this notion of being CPU bound, executing CPU instructions, or being IO bound. And so as you see here, what's being interleaved are cycles of CPU bursts, the running of a CPU bound process. And in this particular case, the CPU bound process becomes an IO bound process because it executes some IO operation. And so you'll see the interleaving, you have a CPU burst, IO burst, a CPU burst, IO burst, and so forth. And so those programs that execute a lot of IO operations are having or getting an opportunity to run, to make progress. And those that are CPU bound are running, but they're also not hogging the CPU. So this idea of load balancing is one way, you're sort of striking the right distribution, if you will, or relationship between the number of CPU bound processes, the CPU bursts, and the IO bound processes. So going carrying through the example, encoding the figure, you wait for IO, right? Okay, so then maybe you schedule another process and its thread is running its main thread and it's going to store something. It's going to maybe iterate through a list using some index, your typical for loop going through an array, and then it decides it's going to write to a file. So all of a sudden, the CPU bound operations, this thread in its owning process becomes IO bound. And so this idea of scheduling is to try to balance this interleaving, if you will, of CPU bursts and IO bursts. And the goal is to try to do so that all programs make some semblance of progress in what they're trying to do, all processes and all threads rather, but you also maximize the utilization of the CPU because you don't want to have it sitting idle. Okay. Any questions about this? Does that make sense? So excuse me, this is the goal of a scheduler. And as you can see, well, this isn't the only way to do it, but someone has taken a histogram of all of the CPU burst times and the number of processes over some run that have a certain burst time. And so as you see here, this graph, it starts out on the horizontal axis, we have the burst duration, and this is in milliseconds. And on the vertical axis, we have frequency. And so that means as you go to the right, your right, on the horizontal axis here, you could call it the x-axis if you want to. I say horizontal. That means that the burst time for that process is bigger, right? So it takes or needs a larger amount of time measured in milliseconds to run. And then the vertical axis here, as you go higher, that says more numbers or counts of processes that run are represented there. So as that graph goes up and to the right, what it says is that as your burst duration goes from zero, which there's no process that takes zero time to run, as it goes from zero and increases in the beginning for small numbers between a burst duration of 0 and 8 milliseconds, you tend to get a larger number of processes that are in that range in terms of the burst time. So what that says is that there are relatively small burst times for threads and processes as they run. And then as you get bigger and bigger in burst time, you'll notice that the numbers get really, really small, about 4 or 5, right? So what that says is that the burst time for any unit of schedulability on your processor is relatively small. And so that's good news, but the bad news is you still need to balance it out. Okay? All right. Any questions about this? Okay. So let's go forward and take a look at, and this part is a little bit of a reminder, the short-term scheduler. And as we said before, the short-term scheduler, short-term, not short-term, short-term scheduler is responsible for taking waiting threads in their processes off of the ready queue and selecting them for scheduling on the CPU. And so that short-term scheduler is going to select one thread, and it's going to say, okay, now you have the CPU. Now, of course, if it's a CPU-bound process, it's going to run, and then eventually it completes, or it executes some I/O operation and is kicked off the processor and joins the wait queue for that associated I/O device. And so there are a number of decisions that take place when you're going to schedule a process or a thread within that process for execution on the CPU. Well, first you can go from the running state to the waiting state. So what that means is, of course, you're done with the CPU and you're going to transition, you being that thread, off of the CPU. Or you could go from the running state to the ready state. So that means you're done with the CPU and now you get to the back of the line, as it were, for the ready queue, because it's trying to give each waiting process or thread some period of time on the CPU. You could switch from waiting to ready, right? So that means that you're now unblocking because you have been waiting for I/O and that I/O operation has completed. So now you get that data from the I/O controller's buffer and you're now put back in the ready queue so that you can get some time on the CPU and hopefully be or eventually be selected by the short-term scheduler. And then of course there's termination. Okay. And so of course we had a state diagram, and there's one in the book that depicts these transitions. Any questions about this? So let's take a look at this notion of preemption. Preemption is the idea that you can be interrupted, right? And so certainly before we said that you're scheduled for execution on the processor, but we didn't say what selection criteria are used to make that decision. That's the job of the short-term scheduler. But in addition, once a process or a thread is running on the CPU, a number of events that could occur to force it to release the CPU, right? It's time for that thread to get off the CPU, regardless of whether it wants to or not, right? This notion of priority. If some higher priority thread comes along that needs service from the CPU, the scheduler can kick some existing process off the CPU and give it to that new thread. And so that completes the picture in terms of the decisions employed by the scheduler. It's not just running until you block or just running until a unit of time expires, and we'll certainly talk about that with round robin scheduling and quantums of time. It also can kick somebody off the CPU if some other event occurs. Okay, and so this idea of preemption is the kicking off of a thread off the CPU. And so when we talk about points 1 and 4 in terms of the transitions that a process can go through, switching from running to waiting state, and also terminating, those two transitions you cannot preempt, right? They just happen and they can't be interrupted. But points 2 and 3, those can be preempted, right? Somebody can come along and sort of get in front of you in line and get access to the CPU, even if you've been there longer or you got there first, right? Life's not fair when it comes to scheduling, and there's a reason for that. And the reason is that, remember, you're trying to maximize utilization of the CPU. And sometimes if you give time to someone else who comes later, the sum total over long periods of time is that you minimize the amount of time that things have to wait, or that processes have to wait, and increasing utilization. So we're going to think about a number of scenarios for preemption, but when you're going to preempt something, you have to be very careful how you do that. So let's say you're trying to access shared memory, right? You gain a lock to shared memory, and then all of a sudden somebody, quote unquote, more important comes along from the scheduler standpoint, and you get preempted. Well, if that new person who gets the CPU needs to access that shared resource and you have it locked, well, they're blocked and you're also preempted, so there's no progress that happens. So you have to exercise care when you're implementing this stuff. And we'll also look at this idea of what happens. Let's say you're running a system call. And when you run a system call, of course, as we had studied, a trap, software interrupt, is triggered, and you transition from user mode to kernel mode. The mode bit is set appropriately, and then the kernel executes on behalf of the user level process. And that's a form of protection mechanism so that you're preventing these user processes, as we had studied, preventing them from accessing directly these critical resources, right? So what happens then if, while the kernel is acting on your behalf, all of a sudden you're preempted, right? Essentially, that progress gets blocked, and especially if the kernel was locking shared resources, there's a problem. Because if your thread is blocked and the kernel is doing something on behalf of you and it's accessing critical resources, then no one's making progress. Okay, and also if you think about interrupts that occur during critical OS activities. So the idea of preemption, it works well in terms of trying to maximize CPU utilization, but you have to be careful where and how you do it, because it might cause more problems than speeding up. It might actually slow things down. Okay? All right, any questions about this? Does that make sense? Okay. So we're going to take a brief look, kind of segue out to Ubuntu, excuse me, and we're going to take a look at some tools, very simple tools, where you can actually look at some system statistics that are kept on the number of context switches that occur. And again, a context switch occurs when the scheduler has decided, for whatever reason, whether it's preemption or quantum based, that a process's time or thread's time on the CPU is done and it's time to let someone else run. And so the context switch counts describe how many times a thread within a process has been kicked off the processor. So there are two, and these aren't the only two, there are two routines in Linux. One's called vmstat, and vmstat gives you all sorts of information about system resources used by every process, including memory pages, including file handles. But we're going to take a look at the number of context switches. And there's also another method using the proc file system. And in Linux, it makes a lot of parts of the machine very accessible to a program by presenting it as if it's a file system. And so when you want to talk to a device, you open up the associated file for that device and you write to that file. It's also talking to that device. And then if you want to read information from some device, you open up that file and you read information. So this proc file system is a special file system in Linux where it presents access to various parts of the machine for you. And it's as easy as reading and writing a file in order to gain this access. And so we're going to look at the proc file system object for a particular process that's running, and you can get the status, and that status talks about CPU time and context switching, virtual memory, and all sorts of stuff. So let's bring up VirtualBox and take a look at these two tools, and they aren't the only tools available on Linux. So let me run Ubuntu. So the usual bootstrap stuff happens. And let me put the commands down here. Okay, make that a little bigger. Login, OSC. Internal error. Okay, well, all right, let me just run a terminal. Okay, that's up. Make that a little bit bigger. Okay, so let's look at VM stat. So if I say VM stat dash S, and we can see a number of things. One of the things you see, of course, you see the number of memory pages swapped in. You look at buffer memory, free memory, total memory, all sorts of stuff. Down at the bottom, the third from the bottom, we have 226,061 CPU context switches, right? So that's an aggregate system measurement. And if you look at the number of forks that were called, the number of child processes that were created, there were 2,722 forks that happened. Now, of course, if I were to run this again, right, it's going to change, right, because it's continually swapping things in, swapping things out. It's preempting things and doing context changes. So we'll look at the number of forks, 2793. Before it was 2722. So we had quite a few forks happen just in that amount of time. And if we look at the context switches, before it was 226,061, now it's 43,136, right? So you had a lot of context switches. And in fact, context switches happen on a millisecond boundaries, right? So they're 1,000 milliseconds per second. So you can imagine in a given second, there are very many context switches. Okay. Any questions about this? Does that make sense? So there's a lot of stuff happening on your system, even though to you it might appear that nothing's going on. But if you think from an operating system's perspective, you have a lot of processes running in the background just to show you what your display looks like, constantly listening for the mouse, listening for the keyboard, and stuff like that. So let's take a look at our processes, PS. Um, and our processes, we'll see in this first column, we see PID, which is the process ID. And so the process ID for the shell, the command line interface that I'm using, is 2485, right? If I were to start another terminal, Control T, and I do a PS again, oops, clear, clear, PS, and actually, you know what? That's just for this shell. PS-EF pipe more. You can see if I list all the processes on the system, right? Each process has an identity. In this case, root, which is the initial login process. There are a couple instances of processes owned by root, and there are also processes owned by OSC. OSC is the user account for the account that I use to log into this. And if I were to scroll down a little bit more, you see that there are many processes like the clipboard, the desktop, all sorts of stuff for the user interface. All these background processes are running. So let's pick a process ID. Let's say 1641. That's called Upstart. That's the thing that bootstraps parts of the user interface. And let's take a look at the number of context switches for process 1641. So let me write 1641. Okay, so let's go to the proc file system, cd proc, and inside the proc file system, you'll see there's some directories that have names that are just numbers, right? Each one of those numbers corresponds to information presented as a file system object, i.e. directory, and their files inside associated with each one of those numbered processes. So I'm going to see if I can find 1641. There it is, 1641. So if I go inside that directory, cd 1641, everything in there is information about process ID 1641, which just happens to be this upstart process. So one of the things there is something called the status, and there's all sorts of stuff like the system calls that you're executing, all sorts of stuff, the group information, limits associated with it, the stack status, timers, all sorts of stuff. But I'm going to take a look at the status, and I'm just going to write out or concatenate the contents of that status file. And so if I do that, I see a bunch of stuff. One of the things I have that I see, voluntary context switches, 748 of them, non-voluntary context switches, 708 of them. So the voluntary ones were ones where it was done with the processor and it went into the wait queue. Non-voluntary are instances when it was preempted, right? So as you can see, those counts are pretty high and they, change very frequently because things, again, after all, run on a millisecond time boundary. Okay? All right. Any questions about this? So you might ask, why you would care about this. If you're working especially in back-end applications, that's database, that's servers, there's things like that, where scalability and throughput is really matters, web servers. What you really want to look at are things like these kind of parameters because they're affected by things like your scheduling algorithm, the quantum of time you give each process, the average burst time, and stuff like that. And part of your job when you're trying to develop scalable servers, especially in this internet age, is to try to tune things like the scheduling because that has a direct impact on the scalability and the throughput, i.e. the efficiency, how much you're working your CPUs, exercising your system. Okay, so these are just two tools among many that are available that you can use to get a sense of how many context switches are happening. So if you created, changed the burst time or changed the quantum time or changed priorities, and you notice that the context switches are happening much more frequently, those counts are getting higher faster, then you might want to make that quantum much larger, right? Because it means that things are switching too fast, if that's important to you. Okay? All right. Any questions about this? Does that make sense? Okay, so let me go back, current slide, and let's continue on. So the dispatcher is that entity that's responsible for physically giving the CPU to some process. And so it's the dispatcher's job to actually switch the context. And that means taking the information, the state of the CPU, writing it to the right process control block or PCB, and then doing the dual operation for the process that gets the CPU, taking its PCB information and populating the CPU with this information. So the dispatcher is the one that performs that work. The scheduler is the thing that makes use of the dispatcher, and the dispatcher performs the actual work of the context switch. The scheduler decides which particular process is going to have be selected. Okay, so the dispatcher module gives control of CPU to the process, and that process is selected by the short-term scheduler, and that means you're going to switch context. You're going to switch to user mode, giving control to that program, and that means also jumping to the right location that talks about the routine where that process is executing. Because remember, one of the pieces of information that goes into the PCB is a program counter, which locates the address, the memory location, where the next instruction is to be executed, so that the program can resume where it left off before it was switched off the CPU. And so there's a quantity called dispatch latency. And the dispatch latency is a really important quantity when you're dealing with high performance servers or servers in general. It's the amount of time it takes for the dispatcher to physically stop one process and physically start another. And remember, stopping a process means it halts the execution and then it copies the CPU state to a PCB, and then it takes PCB information, puts it on the CPU, and then sets the PC, the program counter, and resumes. So that takes time, and the dispatch latency is the amount of time it takes to do that. So here in the figure, this is in the book, you have process P0 and your context switching to process P1. And so process P1 is selected by the short-term scheduler from the ready queue, and process P0 currently has the CPU. And so you start out and you're saving the CPU state, so that's the register file, that's the stack pointer, that's all your memory pointers, it's also the program counter, as well as the text segment and the heap. You save all that information to the PCB for process P0, and then you go and find the PCB for process P1, and then you load all that information onto the CPU, set the program counter, and you're off and running process P1. So all of that takes time, the saving and the restoring of state from the PCB, and together the time that those two steps take, the physical work of stopping one process and switching to another, is called the dispatch latency. Okay. Any questions about this? Does that make sense? Yeah. Okay. So let's take a look at the criteria employed by the short-term scheduler. And so, of course, CPU utilization is paramount. Paramount. And for CPU utilization, you want to keep the CPU busy, working at all times as much as possible. And so you try to make a selection that maximizes this busyness of the CPU. Then you also talk about throughput. Throughput is another piece of criteria employed by schedulers, and that's the number of processes that complete their execution per time unit. And so that talks about the degree of multi-programming. Because if you don't have good throughput, that means not all processes are making progress. And if not all processes are making progress, let's take something as simple as, let's say, you have email running, you have a Skype video chat session running, you have some movie streaming, audio streaming running. If they're not all making progress, then the perception that you get on your machine is all of a sudden something's wrong with your video stream, or all of a sudden something's wrong with your Skype session, or all of a sudden you just can't seem to get email or read email or download files, what have you. And so it's really important to keep this degree of multi-programming high, and throughput is a measurement of that. And they also talk about turnaround time. Turnaround time is another piece of criteria, and it's the amount of time to execute a particular process. And so you also want to make sure each process, in some cases, gets as much time as it can, because the more time you get, the faster your computation will complete. Also have waiting time, right? Now, waiting time, certainly you're not going to maximize waiting time. Waiting time is related to degree of multi-program, because if a process waits, that means it's not making progress. And so waiting time is the amount of time a process has been waiting in the ready queue, and you want to take into consideration this waiting time when you're making a scheduling decision. And then lastly, response time. Response time is the amount of time it takes from when you first submit a process to your system. So that's kind of like you're at the command line, you type a command ls to do a directory listing, and that ls, from the time you type it and hit enter to the time when it actually runs and returns back to you, is called the response time. Because certainly, especially for graphical applications like watching rich media like movies, for things like audio streaming, it's the turnaround time, or rather the response time, that gives you the illusion that things are happening very fast, right? It's responding to you, i.e., doing its work and completing and returning back output to you as quickly as possible. Okay. Any questions about these? All right. So let's take a look at what in particular for these metrics it's going to maximize or minimize. And so CPU utilization, certainly you want to maximize that. You want to keep the CPU as busy as possible over time. Throughput, you want to maximize that. And so again, throughput is the number of processes that complete their execution per unit time. So that maximization of throughput means you want more and more processes to make progress for every given unit of time. Okay. Then also turnaround time. You want to minimize the turnaround time. You don't want things to take a long time to execute, right? You want to give them uh, you want to minimize the time, meaning they run faster. Then there's also wait time. You want to minimize the amount of time that things are waiting. And so what that means is that if you have an interleaving of CPU bursts and I/O bursts, you want to kind of pack that CPU schedule with these I/O bursts, so that those I/O bound processes will turn around faster, okay, and wait less time in the limit over long periods of time. And then also response time, you want to minimize that. You want your processes, or rather the threads running in these processes, to be as responsive as possible, to come back to the user with some sort of response. All right, so let's take a look at scheduling algorithms. And the first scheduling algorithm we'll talk about is fairly simple. It's first come, first serve. Okay, so as the name sounds, the first process that comes along to the system, it's in the ready queue, and in the order in which these processes arrive in the ready queue is the order they're selected by the scheduler. Okay, and so in this diagram, we have a number of processes. P1, P2, P3, so that's the column on your left. And then on the right-hand side, we have the burst time. And the burst time, again, is the amount of time it takes them to run before they come back to the user with some kind of output, but they're not necessarily done executing. So here we have process P1 arrives first, P2 arrives second, and process P3 arrives third. The burst times respectively for P1 is 24 units. You could call it milliseconds if you want to. 3 units for P2, and likewise 3 units for P3. So now, typically with a scheduler, you use a Gantt chart, and a Gantt chart is a software engineering thing, and kind of precedes software engineering a little bit, but it's really just a timeline that lays together items that take time one after another sequentially, so that you can see the relative start time and completion time for some task. And so here on the Gantt chart, on the bottom edge, we see time. And then, of course, these bars for the Gantt chart represent each one of these processes. So in this first come, first serve, we have process P1 arrives first. So at time t equals 0 here, we see that 0 is annotating or decorating the left-hand edge of P1. So that says P1 arrives at the system at time 0. Now, again, we said the burst time was 24. So we see here 24 is decorating the right-hand edge of that block on the Gantt chart for process P1. Okay. So then, once that happens, process P1 has completed. It's done because its burst time is over, and then the next process is scheduled by the scheduler. Now, as we said at the outset, process P2 came second, and it's first come first serve. So now process P2 gets selected by the scheduler using this first come first serve selection criteria. So then process P2 starts. It starts at time 24, and it runs for a total burst time of 3 units. And so we say 24 plus 3 is 27. So at time 27, we see the annotation on the right-hand edge of process P2 as says that P2 is over. It's done, right? It has a burst time of size 3. And then at 27, we have process P2 is done, and now process P3 had come third on the ready queue. And the scheduler in this FIFO order, first come, first serve, it selects process P3 for execution. So we see here at time t equals 27, process P3 runs, and it runs for a burst time of 3 units, and it completes at time t equals 30. So here we have process P1, followed by process P2, process P3. The Gantt chart describes how they are selected for execution, how long they execute, when they start, when they end, using this first come, first serve selection criteria. And so if we were to look at the wait time, one of the things you might be concerned about is to minimize the wait time. And one way to talk about the wait time is to look at the average wait time associated with a particular scheduling discipline or scheduling criteria. All right, so if we do that, well, let's look at the wait time for each of them. So process P1, they all arrived at the system, one after the other into the ready queue. Process P1 ran immediately. Its wait time was 0. But process P2, it had to wait 24 units before it was started, so its wait time is 24. And process P3, it had to wait for process P1 and process P2, so it had to wait a total of 27 units or milliseconds, if you want to call it that, before it started to run. So if we take the average of these, 0, 24, and 27, we get an average wait time of 17. Okay? All right. Any questions about this? All right. So this is first come, first serve scheduling. And let's take a look differently at what happens if the arrival order for first come, first serve is different from that P1, P2, P3. In this augmented version of first come, first serve, let's assume that P2, P3, and P1 arrived at the first come, first serve schedule at the ready queue in that order. So you have P2, P3, and P1, not P1, 2, and 3, which was the example before. So if that's the case, okay, P2 comes in first. And remember, and it's the same burst times from before. It had a burst time of 3, so P2 arrives first. So it's run for a total of 3 units. That's its burst time. And then P3 runs because it arrives second, and it has a burst time of 3, so it runs. And then after P3 is done, P1 executes. So it starts at 6, and it runs for a total of 20. It was 24 units, and then it completes. And so with this different arrival, right, of P2, P3, P1 versus the P1, P2, P3, we do the same calculation with the average wait time. And so the wait time for P2 was 0, okay. The wait time for P1 was 6 because P1 ran after 3 and 3. and then the wait time for P3 was 3, right? So we add those three together, take the average, and now we have a much better wait time. We have a wait time of 3 units. And so what this just says is that if you can alter the order in which processes are selected, you can dramatically reduce the wait time. In this particular case, just by running P2 and P3 before we ran P1, the wait time now went down to 3 units, whereas before, if we execute them P1, P2, P3, the wait time is 17 units, right? So that's a dramatic decrease in minimizing the wait time. So people enterprise to try to have alternate selection criteria so that even if they arrive in a certain order, you employ other things than just the order in which you arrive as your selection criteria. And this proves it that a different selection criteria can often lead to a dramatic savings in the average wait time. Okay. Any questions about this? Does that make sense? Okay. Now, remember, when we talk about average wait time, this is to maximize the system. All right. This doesn't talk about the experience of a process. It's the system itself. Okay. All right. Any questions? Yes. Sure. This one. hmm The average went from 0 to 3. And so the average went from 0 to 3 because let's go back to the first one, right? And so in this first come, first serve, in time, P1 arrived first, then P2 arrived second, and then P3 arrived third. And so if you had this arrival order, P1, P2, P3, in the first come, first serve selection, the first thing it's going to select is P1, and then this first next thing it's going to select is P2, and next thing it's going to select is P3. So that being the case, when it runs P1, P1 takes 24 units, right? And that's where the biggest contributor was to the larger average wait time in this scenario, right? So everything else that comes after P1 has to wait at least 24 units, right? And then P3 had another 3 on top of that 24. But in this next example, we change the order, right? And let's imagine now, instead of going P1 first, P2 second, P3 third, we have P2 arrives first, P3 arrives second, and P1 arrives third. And by a first come, first serve, you're going to execute them or select them from the ready queue in the order in which they arrive. So if P2 came first, it runs P2, so it does not wait. So there's a 0 wait time for P3, and then for P2. And then P3 is scheduled second, right? P3 has to wait 3 units, right? Because it has to wait for P2 to complete, and it runs for 3 units. And then P1 runs, and P1 takes 24 units to run, but it only has to wait 6 here. And so if we take that average by selecting the smallest task in terms of burst time first, we can actually, or changing the order of execution, we can actually minimize the average wait. And so here, this savings is because you rearranged which one you're going to run first, which one you run second, which one you run third. Now, a better diagram would have been to say P sub I, P sub J, P sub K, right? Instead of saying 1, 2, 3, and then changing the order because it's kind of a little bit confusing when you see it the first time. Does that answer your question? Yeah. Any other questions? No? All right. So what this says is by changing the order of execution, you can dramatically decrease the average wait time. And that's a great criteria to try to make maximum utilization of your CPU, because if your average wait time is small, that means your CPU is working more of the time. Okay, so let's continue. So kind of piggybacking off of that idea, there's another scheduling approach called shortest job first. And what that shortest job first does is says it takes each process and it associates with it a number, and that number is directly proportional to the length of its next burst. And so the idea is when the scheduler is going to select a process from the ready queue for execution, it's going to select a process that has the shortest burst time. Okay, and as we saw here in the previous example, by selecting the shortest burst time, we went from 17 units of average wait time down to 3 units. So that's where the shortest job first scheduling discipline or scheduling criterion came from. And so Shortest job first, it's optimal, meaning that it gives the minimum average wait time for a set of processes, right? By having things wait longer, you're sort of amortizing the cost of how long it takes to execute something long by just waiting small amounts of time, and you're actually making more progress. And we actually saw that play out. So this is optimal, and what it does is it gives you the minimum average wait time, and we actually saw that as a real example. And so now this is difficult for one reason is that how do you determine the burst time, right? Certainly, when you schedule some process for execution on the CPU, you can measure how long it takes before it's done running, right? So you start it running on the CPU, you set a stopwatch or set a timer, and then you stop that timer when the burst is over, right? So when it goes from a CPU burst to an IO burst, or when it goes from an IO burst back to a CPU burst. You can associate timers with that and absolutely measure the burst time. So then you can make the assumption that, okay, if the burst time was 3 units or 24 units last time, it's probably going to be 24 units again the next time. And you can also kind of tinker with that number and use the latest measurement to kind of move the value of what your running total is. And we'll see a little bit about that in the next few slides. Okay. Any questions about this? So this is shortest job first, and that shortest is determined by the burst time, and you can calculate that burst time with a timer and just measure the time that CPU burst or IO burst takes to execute. Okay, so here's an example of shortest job first. And in this particular case, you have 4 processes that arrive in your ready queue, and they're there. And process P1, P2, P3, and P4. Process P1 has a burst time of 6 units. P2 has a burst time of 8 milliseconds. I'm going to say milliseconds and units as synonyms. So we have 6 milliseconds, 8 milliseconds. P3 has a burst time of 7 milliseconds. And lastly, P4 has a burst time of 3 milliseconds. So now we have P1, P2, P3, P4 in the ready queue, and the scheduler is going to make a choice of who to put on the CPU next. So by shortest job first, we look at the burst time, and we select P4 for execution because it has a burst time of 3, which is the smallest burst time, not birth time, burst time among all of the processes that are in the ready queue. So P4 gets scheduled for execution, and it does not wait. It starts at time 0, right? And it runs for 3 milliseconds, and at 3 milliseconds, P4 is done. So now P4 is done, and now the next process is selected for execution. So the dispatcher is going to be the one that takes off the PCB information and then puts new PCB information onto the CPU. But first, the scheduler running this shortest job first criterion selects a new process. So P4 has just completed, and then it looks at the burst times among the others that are still there in the ready queue. And it looks and it says, well, process P1, that has the shortest burst time. So it then selects process P1. The dispatcher then switches context from P4 to P1. So now P1, it started at time 3 because that's the time when P4 exited the CPU. And P1 runs for a total of 6 milliseconds. So it starts at 3, it completes at 9, and after that, the scheduler says, okay, well, let me make another selection. So P1 and P4 have executed, and it looks at the remaining processes on the ready queue, not the remaining, the others are back on the ready queue, but it looks at the other 2 processes and says, okay, well, P3 is the next shortest burst time. So it runs P3 for a total of 7 seconds. It starts at 9 and ends at time 16, and then it takes the next one, which is the remaining one which on this list, which is P2, which runs for a total of 8 milliseconds. Okay. Any questions about this? Does that make sense? Yeah. Okay. So if we look at the average wait time, we'll see that, okay, well, process P4 had a wait time of 0. So there's my 0. Process P1 had a wait time of 3. So there's my 3 here. Process P3 had a wait time of 9. So there's 9. And process P2 had a wait time of 16. So I take those numbers, add them up, take the average, and I have an average wait time of 7 milliseconds. Okay. Any questions about this? So if we were to do this first come, first serve, that'd be a great question. How does that algorithm, when you go from first come to first serve, how does that change the average wait time, right? And you can actually see if process P1 came first, P2 came second, P3 came fourth, P3 came third, P4 came fourth. Well, you would have a wait time of 0, 6, 14, and then 14 and 7 is 21, right? And you notice that that average is much higher. Okay. All right. Any questions about this? So the scheduling discipline, as it's called, the criteria employed by the scheduler, whether it's first come first serve or shortest job first, can dramatically impact the average wait time. Okay. So no questions, then I'll just move on. All right. So one question that arises is, okay, well, this shortest burst time can lead to a dramatic savings in average wait time, but how do you know what the burst time is? I alluded to the fact that you can start a timer and stop a timer and actually measure the burst time. And then you can also take this running total and nudge it a little bit based on the most recent burst time. And what it does is exponential moving average, which is something from Financial Times series. And so you can only estimate the length of the burst time from actual burst times. You start out with just 0, and then it runs, and you have a timer value. And then the next burst time, because it might be a CPU burst or an IO burst, it might be a little bigger, might be a little smaller, might be a lot bigger, might be a lot smaller. So you need to keep a running total that is an estimate, as it were, based on these measurements, your stopwatch, and you update this as this thing continues to have a CPU burst or an IO burst, this thing being your process. And so you pick a process then with the shortest predicted burst time, and then you're updating these burst times as time goes on. So this can be done by using the length of the previous burst, and this is in the book. Here, they're using notation T sub n as the length of the nth CPU burst. That's the most recent burst. You run something, you you finish the burst, and then you stop the timer, and there's your T sub n, right, for the nth time that you run it. And this tau of n plus 1 is the predicted value for the next burst. So you're going to take the current burst and use that to predict what you think the next burst time would be. And then you have this alpha, and alpha is something called a mixture component. And what alpha is going to control is when you predict the next burst, that next burst prediction is going to be some proportion, a little bit of the previous prediction, plus a little bit of whatever the current measurement is, right? And so your predicted burst is a little bit more stable than just using the current measurement each time, because the current measurement can swing high, swing really low, right? It can be very big, very small, very big, very small. But when you do a prediction, you want that prediction not to change as dramatically as the measured quantity. So here, this definition, tau n plus 1, which is the next prediction of the burst time, what it should be, is going to be alpha, where alpha is between 0 and 1. So it's going to be some proportion of the current measurement, right? The starting and stopping of the stopwatch, plus some complementary proportion. So if alpha is like 0.2, that means 20% of the current measurement and 80% is the previous prediction, right? So we have alpha, some proportion of the current measurement, T sub n, and we have 1 minus alpha, which is sort of the remainder, if you will, as a proportion of the previous measurement. So the next measurement is a little bit of the current measurement plus a little bit of the previous measurement. And commonly, alpha is 0.5, right? You kind of say the next measurement is half the previous measurement and half the previous prediction. Okay? All right, any questions about this? Okay, so this there's a preemptive version of shortest job first. And what this preemptive version does is it takes a running total and it says, okay, well, if a new job arrives and that new job has a shorter estimated burst time, I'm going to kick the currently executing process off the processor. So now we're going to add preemption to this. But let's first look at what the predicted burst time, tau, how that relates to the measured burst time, t. Now remember, you have a process that runs, so it has a burst time at one moment, and then another burst time, and then another burst time. Here on this graph here, on the horizontal axis, we have time increasing to the right, your right. And on the vertical axis here, we have burst time, right? And this T sub I, the actual measurement, That's going to be this black line, right? And you'll notice here for the first few milliseconds, the burst time is measured as 6, and then it goes down to 4, then it goes up to 6, goes down to 4, and then it jumps up to 12. Not 12, 13. Um, and so you'll see this burst time for every period of time when this process is on the CPU. It's constant, but it can change from one burst to the next. So you can imagine you have a CPU burst followed by an IO burst, followed by CPU burst, followed by an IO burst, and so forth. So the burst time can change. But this tau here, which is the blue graph, this tau is computed using this exponential moving average. And what it does, it says, okay, well, I know that if the measured quantity decreases, I want to decrease my estimate, but I don't want to decrease my estimate as vigorously as the measured quantity. I only want to decrease it a little bit based on the decrease in the measured quantity, but it's still going to maintain some semblance of its old value, right? And so it's a little bit smoother, and as you can see here in the blue graph, here, when the measured quantity goes from 6 to 4, that's a really abrupt change in a very small amount of time. This estimated quantity decreases at a much slower rate, right? It still decreases, but it's not quite as rapid as the actual measured quantity. And the reason why that's a desirable property is because when you're basing something like scheduling on some quantity that you calculate, if your quantity keeps jumping up and down, up and down, up and down very quickly, your system is going to do what's called jitter, right? It's going to make a decision in one extreme, and then all of a sudden make a decision on the other extreme, and that's not good for your system, right? Bad things will happen. And so here, as we see, for example, in this increment of time, our burst time goes from 4 all the way up to 13. We see an increase, but the increase in your predicted quantity, this blue line, tau, it's much smoother. It eventually gets close, but it doesn't jump quite as quickly. And so if you're going to do preemption, you want to have smooth movements in your predicted burst time, because if you're going to interrupt somebody and switch to something, you don't want that thing you're using to base the interrupt on. You don't want that to change too rapidly, because you're going to get a lot of jitter in your system. Okay? All right. Any questions about this? Okay. So let's take a look at this exponential average. Now, this alpha is a mixture, and if alpha is 0, that means the recent history, the actual time measurements, your stopwatch starting and stopping, isn't going to come into play. You're going to have this running estimate, and that estimate is going to stay the same, and it's not going to include any measurements. So if you think about it, what this estimate is doing, it's saying, okay, well, I have this estimate of the burst time that I always have available, and I'm going to let this estimate be influenced by current samples of the burst time. And so that kind of makes sense, right? You have this quantity that you're using to base your decisions. It doesn't change as rapidly, but its value is going to be influenced some little bit by the actual measurement. And that's a nice property. So if alpha is 1, it's the converse. If alpha is 1, that means only the last CPU burst is what counts. So alpha equals 1 says this burst time estimate is going to be exactly the most recent measurement. So what ends up happening for alpha equals 1, well, this t sub I is exactly what this t is, and it's going to jump and have these discontinuities and make some very short-sighted decisions when it's doing this shortest burst time first selection criteria. Okay. And if we expand this formula, right, and it's called exponential average, because each time you unwind this expression, if we take a look at this expression, if we apply it again, well, let's see. Here we have tau n plus 1, here we have tau n. Now, tau n, if we have n here, this is going to be n minus 1 and n minus 1. If we apply this again and again and again, what happens? Well, we're multiplying by alpha again and again and again, and we're also multiplying by 1 minus alpha again and again and again. And so when you multiply something by itself multiple times, that's the same as exponentiating. And if this alpha is between 0 and 1, what ends up happening is that you end up tailing off the contribution so that it kind of only uses measurements up to some period of time into the past to influence what the future value is. And so here in this chart or this slide, and this is in the book, here they say, what's the definition of tau n plus 1, the estimate at time n plus 1? Well, that's just alpha times n, 1 minus alpha times tau at n at value n. Well, tau at value n, if I substitute what that formula is, this recurrence relation, I get this expression, and then this expression, and this expression. And one thing you'll notice here is that this 1 minus alpha is exponentiated, increasing number of times based on the number of times that you apply this recurrence for that value, substituting what that is. Okay? So if you keep doing that, keep doing that, keep doing that, what ends up happening as this equation gets unwound another time, another time, another time, this 1 minus alpha increases in exponent. And what that increase in exponent means is that an actual measurement further back in the past gets weighted by a smaller and smaller number. And if you have some quantity that's less than 1 and you exponentiate it a certain number of times, eventually it goes to 0. And so what's that saying is that I want to count 1 minus alpha many times, the measurement one step in the past, 1 minus alpha to the 2 power many times, the measurement 2 steps in the past, and then 3 steps in the past, 4 steps in the past. And each time you take another sample measurement going further back in the past, the amount that it counts in terms of the prediction is less than and less and less. So you can think of that as a kind of memory where it's forgetting the distant past, but incorporating or remembering measurements for the recent past in terms of the prediction of what this future value is. Does that make sense? This is something that's used in time series all the time, and it's called exponential weighted average because of this property that when you apply this successively over time, this exponent increases, kind of giving you this memory. How much of the recent history should you count in the future value? Okay. Any questions about this? Make sense? Okay. So let's take a look at this preemptive version of shortest job first. Now, this is the same shortest job first criteria that we had before, only now we're going to add preemption. So that means if a new process comes along that is shorter than the remaining burst time, then you're going to stop what you're doing and context switch to that new process. Okay, so here we have our chart. We have 4 processes, P1, P2, P3, and P4, and they arrive in the ready queue at the following times at T0, time 1, time 2, and time 3 milliseconds. And P1 has a burst time, and that's that right-hand column, of 8 milliseconds. P2 has a burst time of 4, P3 has a burst time of 9, and P4 has a burst time of 5. So the center column here, arrival time, is when they appear in the ready queue. That last column on the right, your right, is the amount of time it takes to run, this burst time. And so let's see what happens in this preemptive version, and we look at the consequence of what this preemptive version is. So we start out, P1 arrives at time 0, and at time 0, it's the only process, so it immediately gets scheduled. And so P1 is running, and so 1 millisecond transpires, and if 1 millisecond transpires, it now has a burst time remaining of 7, right? And so at time 1 rather, process P2 comes along. Now when process P2 comes along, P1 is 1 second into its running, right? So you can think of that as P1 having 7 milliseconds of burst time left, but when P2 arrives, its burst time is smaller than what's currently running, right? So it decides, okay, well, I'm going to preempt P1, and I'm going to select P2 because at the moment now, once P2 arrives, its burst time is 4, but the original burst time for P1 running is 8, and it is 1 second into that running. Okay, so P2 gets scheduled, and P2, with its burst time of 4, it starts to run. Okay, so P2 is running. It starts at 1. P1 is now kicked off. It's been preempted. And so P2 runs for a total of 4 seconds. Okay, so what happens at time 2, right? So at time 2, P3 comes in, and P3's burst time is longer than P2, so P2 continues to run. At time 3, P4 comes in, and P4's burst time is larger than P2, so P2 continues to run. But if another process came along that had a shorter burst time, P2 would be kicked off the processor. So for that reason, P2 continues to run and it runs to completion for a total of 4 milliseconds, and it completes. So now, at that moment, at time 5, P1 has been kicked off, P2 has completed, and P3 and P4 have arrived. So now you have P2 is done, so it's not going to be considered. And P1, that has been kicked off, and it had an original burst time of 8, and it was done with 1, so you could think of it as needing 7 more to complete. P3 had a burst time of 9, and P4 had a burst time of 5. So at that moment, you have burst time of 7 remaining, 9, and 5. So P4 gets selected for execution, right? Because it has the smallest burst time of those processes that remain. So P4 gets scheduled for execution, and it runs for a total of 5 units, and it still has the smallest burst time, so it is allowed to continue and to complete, and it completes at time 10. So now P4 is done, and you're left with P1 and P3. Now P1, it had a burst time of 8, and it ran for 1 millisecond, so it has 7 units remaining, and therefore it is smaller than P3's burst time, which is 9, so the system schedules P1. So P1 continues its execution, and it runs for 7 units. So here it starts at 10, and it ends at 17 because it had already completed 1 before it was preempted with the arrival of P2 and P4. So now P1 finishes at 17, and then what's left is P3, and P3 starts at 17. It runs for 9 units and finishes at time 26. Okay, does that make sense? The schedule, the Gantt chart? So with this preemptive version, if a new process arrives to the ready queue and its burst time is less than the burst time for all the processes in the system, including the one that's on the CPU, it gets preempted, it gets kicked off the processor, and the shortest burst time runs. Now this is different from shortest job first. This is a preemptive version of shortest job first. The regular shortest job first does not preempt, but this version can kick someone off the processor if a shorter one comes along. Okay, so if we look at the average wait time, okay, well, we have P1 comes in, and it, let's see, let's see, one, so I just had a brain fart. Let's see, point one. Okay, yeah. Okay, so um, so process P, what is it, P2? Let me start with P2. P2 ran for 4. P2 arrived at, where was it? Oh, I did this last night. I can't remember what I did. Oh, let me think about this. 5, first time of 5, arrival time of 3, started at 5. Okay, yeah. Okay, all right. I'm back. So P, let's take this term. P, 4, it started at 5, right? At time 5, right? But it had an arrival time of 3, right? So if you were started at 5 and you had an arrival time of 3, that means you waited for 2 milliseconds. Okay. So here, P3 started at 17, right? No, rather, let's see, 17, P3, 17. Yeah, P3 started at 17, all right, and it entered the system at time 2, so it had a wait time of 17 when it was started minus 2 when it arrived, so it had a wait time of 15, right? So that's a 17 minus 2 comes from. Okay, so P2 arrived at time 1, and it was started at time 1. Okay, so that's good. So its wait time was 0, right? And here, the last one, um, P1, it had a start time of 10 and had an arrival time of 1. And where that 1 comes from, um, it counts the arrival time of P1 as that time when it was preempted. Because when it's preempted, it got kicked off the CPU, re-entered the ready queue, and they count the arrival of P1 as that time when it entered back into the ready queue. Okay? So for P1, it was started at time 10, and it arrived at this point, because they're not counting this part here, at this point when it went back into the ready queue because it was preempted. So if we add all those terms up and divide by 4, the average wait time is 6.5 milliseconds. Okay, so that makes sense? And so this is the same as regular shortest job first, except, and this is an important nuance, is that you can preempt if a shorter job comes along after the fact. Okay? All right. Any questions about this? Make sense? All right. So let's see what time we have. We have about 4 more minutes. So let me just motivate this, and then we'll pick back up on Thursday. And so priority scheduling has a priority number, and that priority number is associated with each process. And shortest job first, you can think of it a little bit as implementing priorities, but it's fixed to the idea of a job, right? And so what this priority-based scheduling does is it associates a number, its priority, and it kind of decouples how you compute this priority from the fact that it's employing a priority to do the scheduling, right? Shortest job first preemptive is taking the burst time specifically as how it assigns the priority. But if you assign a number like 1 or 5 or 7, you can use any method or any metrics, if you will, to decide what a priority should be. And so when we meet next time, we'll talk about this priority scheduling. And there are different ways of implementing it, because one of the concerns that you have with priority scheduling is that if something higher priority always comes along, the lower priority items get starved out. And you want to make sure that you're going to give some time to the lower priority tasks, because everyone needs to make progress to have a high degree of multi-programming. Okay, so if there are no questions, we'll end here and pick back up on Thursday from priority scheduling, hopefully complete the module by the end of the week. All right. I'll see you all on Thursday.